Hello, welcome to today's lesson on section 6.2, which is titled Apply Properties of Rational Exponents. So we talked about the properties of exponents in the previous unit, but I probably should bring it up again. So here I'll state the property, and here I'll give an example. So the first property will be something like this. In this case, we're allowed to add the two exponents together. So for example, if I had 5 to the 1/2 power times 5 to the 1/3 power, I could just add those together. And if you add those together, you should get 5 to the 5/6 power, because that's what 1/2 plus 2/3 will add up to. If I have something like this here, you multiply the exponents. So if I had like 5 to the 1/3 raised to the 4th power, it would be 5 to the 4/3 power. So just because you have fractions as exponents doesn't mean that the same rules don't apply. So you could use the same rules. Or if I had something like this, then I would subtract the exponents. So if I have 5 to the 4/5 power, or 5 to the 3/5 power, the answer would be 5 to the 1/5 power. Three more properties I want to state. If you have something to a negative exponent, you just put on the bottom. So if I had like, say, 4 to the negative 1/3 power, it would be 1 over 4 to the 1/3 power. If I have something like this with parentheses, you simply distribute the exponent to both a and b. So if I had, say for example, 16 times 9 to the 1/2 power is 16 to the 1/2 times 9 to the 1/2. And lastly, number 6. If I had this, a would be raised to the m power. Again, distribute the m to both a and b. So if I had, say, 8 or 27 raised to the 1/3 power, be 8 to the 1/3 or 27 to the 1/3. So those are the main properties. Now we're ready to try some examples. Actually, before that, another thing I want to talk about are properties of radicals. So if you have something like this here, the nth root of a times b, you can separate them like this. Because if we think about it, it's like what a times 1 over to the n power times b raised to the 1 over n power, which is very similar to that property right there. because the nth root of a times b is like a times b also raised to the 1 over n power. Another thing, if you have the nth root of a over b, it's the same thing as taking the nth root of a over the nth root of b. Of course, assume b does not equal 0, since you don't want it to be undefined. Because again, it's like saying a over b raised to the 1 over n power equals a to the 1 over n times b raised to 1 over n. So it's just like that, which actually utilizes that property right there. So I think now we're ready to do some examples. So in each example, we want to simplify. So for each example, simplify the expression. So here's our first example. So you have the third root of 12 times the third root of 18. So if we think about it, we can just put it all underneath one cube root, since they're both being cube rooted. So it'll be the cube root of 12 times 18, which is 216. If you work it out, you should get 6. Or for number 2, say I have the fourth root of 80 over the fourth root of 50, fourth root of 5, I can write as the fourth root of 80 over 5, which is the fourth root of 16, which just equals 2. Okay, let's look at some more. What if I have the third root of 135? Well, here's the thing. If you do a prime factor tree, do a prime factor tree, you start with 135, and you start branching it off. So you have 3 and 45, and you have 5 and 9, and 9 breaks apart as 3 and 3. So if you think about it, 135 equals 3 to the 3 power times 5. So then when you cube root it, we can break it apart as the cube root of 3 cubed times the cube root of 5, which is 3 cube root of 5. So instead of square rooting, we're cube rooting, so now we're looking for 3 equal roots. So we want to look for 3 equal roots, which we had here with the 3, the 3, and the 3. Another problem I'd like to look at is this one here. Say we got ourselves the fifth root of 7 over the fifth root of 8. Well, eight is 2 times 2 times 2, right? So in this case, we want to rationalize the denominator. And remember, rationalize the denominator means make denominator a rational number. And also remember that rational numbers, any number that can be expressed as a ratio of two integers. If you actually were to work out the fifth root of 8, that'd be a really weird number. And 8's not a perfect fifth root, so you're not going to have a rational number there. So we want to make it rational. So in order to do that, you want to introduce two more 2's. So you want to introduce two more 2's, because right now we have 3 2's with 8, but if you introduce two more 2's, then here's what you can have on the bottom. You're going to have the fifth root of 7 times 2 times 2. On the bottom, we're going to have the fifth root of 2 to the fifth power, which just makes the bottom 2 now, and the top will be the fifth root of 7 times 2 times 2, which will be 28. So now you have that. A couple other problems I want to talk about. So that was our fourth example. Example 5. So I think now we're ready to try some stuff with variables. So what if I have this? The cube root of 64 y to the 6th power. Well, we know we could break up like this. Cube root of 64 is 4. And the cube root of y6 is y squared. So the answer is 4y squared. So even with variables, you still apply the same rules. Let's try another one. 27 p cubed q12, the whole thing raised to the 1/3 power. So you raise the you distribute the 1/3 to every part of that expression. Notice how I multiply 3 to 1/3 and 12 to 1/3. So you get 3p q to the 4th power. Let's look at number 7. Say I have the following: 14 xy to the 1/3 over 2x to the 3/4 times z to the -6th power. So you will first want to do 14 divided by 2, which is 7. Then you want to do x to x to the 3/4, which is x to the 1/4. The y to the 1/3 stays where it is, and the z6 comes up top. So there's nothing left in the bottom, so you put a 1. And notice again how x is x to the 1 power, so I subtracted those exponents. So I just get 7 x to the 1/4, y to the 1/3, z to the 6th power. We'll do 3 more examples and I'm finally done. What if I had the fifth root of 4a8 b14 c5? Well, if you think about it, you can write like this: fifth root of 4 times fifth root of a8 times the fifth root of b14 times the fifth root of c5. Now, fifth root of 4 is really nothing we could do about that. But here, a8, since you have 5 a's, you can write like this: a to the 5th times a cubed. And you can write b14 as b to the 10th times b to the 4th. And of course you have the fifth root of c5. So now I can rewrite this as fifth root of 4 times a fifth root of a cubed times b squared fifth root of b4 times c. So basically I pull an a, b squared, and c, because 5 goes into 8 once, 5 goes into 14 twice, and 5 goes into 5 once. So you have a, b squared, c times the fifth root of 4 a cubed b4. Number 9. What if we had the following? One-fifth root x plus 3/5 root x. Well, in that case we just combine like terms. So because you have both 1/5 and 3/5 multiply the root x, you just add the 1/5, 3/5 together and keep the root x. So we'll try another one that's kind of close to but a little bit more complex, and then I swear we're finally done. Let's say we have something like this here. 12 times the cube root of 2z5 minus z times the cube root of 54z squared. Well, looking at the first radical, you have a cube root of 2z5. 3 goes into 5 once, so you pull z out. You have cube root of 2z squared minus z times, now 54, and it was 27 times 2. And cube root of 27 is 3, so you have 12z cube root of 2z squared minus, take the 3 out, 3z cube root of 2z squared. Notice how cube root 2z squared is a like term, as well as a 12z and 3z. So really it's just going to be 9z cube root of 2z squared. And that's number 10. So if you have a chance to practice this, you know, this is kind of a crazy thing here. So again, you'll have a chance to work this out. And that's that. So I will see you guys next time in class.